All right, so let's start today's seminar. First of all, welcome back. This is the third seminar on ANN search. Okay. Um, Today we are ready to talk about the query time of approximate graphs. Okay, and um, we have been using disk ANN as the representative for proximity graphs. Okay, so we will talk about the query time of disk ANN. Okay. Well, so far we have not really formalized the notion of query time of proximity graphs yet. Okay, so I have already explained to you what is a 1 plus epsilon uh, proximity graph. So this is a proximity graph on which the greedy algorithm always returns a 1 plus epsilon approximate nearest neighbor. However, the thing is, not every proximity graph uh, promises fast query time. Okay. In order to illustrate this, let's look at an example where this P is a set of points, um, in one-dimensional space. Right. Just think about any set of points like this. We can build a proximity graph on this set of points as follows. You simply sort them, let's say like this. And now I want you to chain them up from left to right. Okay. And also I want you to create another edge, uh, backwards, right? So opposite direction. Okay. So basically, you connect every two consecutive points bidirectional. Okay. All right. And you can verify for yourself if you have any query point. Let's say the query point is here. Now remember, this Q is also a one-dimensional point. Okay. So if you have any query point, then you can start from any vertex in this proximity graph, and you can verify that the greedy algorithm will always return you the exact nearest neighbor. All right, so the exact nearest neighbor. Okay. However, this proximity graph is not. It could be very slow, right? Because in the worst case, if I have this query point at the very end, right? If I force you to start from the leftmost point, and then the greedy algorithm would have to traverse uh, through the entire chain in order to return the exact nearest neighbor, right, from left to right. Okay. So now proximity graphs. It's not necessarily fast. So we need a notion. Okay, so we need a notion to define what it means by the query time of proximity graphs. Okay, and then we will utilize the notion to analyze the query time of disk ANN. All right, so that's what we are going to do today. Okay. All right, now let's first define the query time of proximity graphs. Okay, so let's recall the greedy algorithm. Okay, so the greedy algorithm says, in general, you give me a start point, right? So this P star, and also, a query point Q. Okay, any query point Q in the metric space. And the greedy algorithm will always return you a returnable answer, right? A returnable answer being a 1 plus epsilon ANN. Okay. But the thing is, this greedy algorithm might take forever to finish, right? And you have to understand, even though the greedy algorithm has not finished, the point that it currently stands at could be a returnable point. Okay, so these two are two very different things. One, the algorithm has not finished yet; it's still running, and two, it has already found a returnable point. All right, so these two things, they are different. Okay, simply because the algorithm still has to run does not mean that the algorithm is able to return the best point found so far. Okay, so the query time notion that I'm going to introduce captures this intuition. Okay, so here I would define a very similar function, which I would call a query. Okay, so this query takes, again, two parameters, right? The start point and also the query point. And also, in addition, it also takes a budget. All right, so this is an integer here. This is the budget. So this budget basically tells you how many distance calculations you are allowed to perform in the greedy algorithm. Okay, so this query algorithm says the following: if when the algorithm is running, if the number of distance calculation is less than or equal to q, and then what you want to do is you just do what greedy has to do. Okay, but on the other hand, if the budget has been exhausted, and then you will have to return, this query algorithm will have to terminate greedy by saying, I have to return the point that greedy is standing at. It is standing at. Okay, so in other words, I don't care if you still have our neighbors that you have not processed yet. I don't care. All right, you have to stop right here, and you have to return the point you are currently at. Okay, no matter what. All right, so this is the new query algorithm. It's sort of like a trimmed version of greedy, right? Because I trim you, I set a hard limit on how many distance calculations you can perform. Okay, so I trim you right there, and you have to give me the best you have at that moment. Okay, so we say that a proximity graph guarantees query time Q if this algorithm, the trim version, always returns a legal answer, right? A 1 plus epsilon nearest neighbor. Okay, good. All right, so with this thing understood, next we will start to analyze the query time of disk A and N. In the previous two seminars, we have talked a lot about this interesting method, right? So one particular interesting thing to note is the following. Okay, so we are able to, guarantee this shortcut property. All right, sorry about that. Okay, so this ANN, as we already know, guarantees the shortcut property. Okay, so for the shortcut property, my favorite way to explain it is to ask you to look at a figure. All right, so let's say you've got this P here, and also you have your final destination V. Okay, and now suppose you don't really have an out edge directly to V. All right, if that is the case, and then this distance here will have to be strictly less than 1 over alpha, okay, times the distance, from P to V. Okay, so in other words, you have an out neighbor. So by going to your out neighbor, you are able to reduce your distance to the destination by at least a factor of alpha. So we will still set the value of alpha to 1 plus 4 over epsilon. All right, so this is the value chosen before. Okay. Now, to explain our result, we will also need this d min and d max. So this d min is the smallest, okay, interpoint distance in our data set P. Okay, and this d max is the largest. Okay. All right. So this d min is greater than 0, right? Because by our definition, if 2 points are different, and then the distance will have to be strictly positive. Okay, so pay attention, right? So this d mean is the smallest inter-point distance, right? So they have to be the distance between two different points. And we define this delta to be the ratio between d max over d min. So this is the aspect ratio. Okay. And we also have this lambda, right? So this lambda is the doubling dimension of the underlying metric space. So today our discussion is under the assumption that this doubling dimension is small. In other words, this is some small value that absolutely does not depend on the size of the data set. Okay, so it can be regarded as a constant. And if this assumption is not satisfied, and then the analysis does not hold, and then we don't really have an explanation for the excellent performance of this ANN in practice, right? But if it does hold, and then this would be a plausible explanation. All right, so from the last lecture, we know that every point, in this proximity graph constructed by this ANN, so every point has out degree. How much? This is no more than 1 over epsilon to the power of lambda and then log delta. All right, this is something we proved last time. Okay, good. Now, this is where we are currently. Okay. So today our goal is to prove this Graham theorem. All right, so this theorem says, this GDA, okay, ensures, guarantees query time. This Q, this is big O of 1 over epsilon lambda, okay, log square delta. Okay, so this is the theorem that we try to prove today. Okay, good. All right. Well, in order to prove this theorem, the approach we're going to take is the following. So we will prove, this is sort of like the real goal. Okay, the goal is to prove that this ANN, okay, finds an acceptable, returnable point after, how many hops? After log delta hops. Okay, so this is, our real goal. All right. Well, as you can see, if this is something we can prove, okay, and then I'm going to set this Q to this value here, okay, to this value. Let's say at least so many values. All right. Now the thing is, if Q is equivalent to this value, as you can see, it's at the order of this 1 over epsilon to the power of lambda log squared. Okay, and since every point will require me to calculate, so many, as you can see on screen, right? So many distances. And then if my budget is so much, and then I know that I get to access at least log delta points, right? At the order of log delta points, right? So as I said, if this goal is true, and then I guarantee myself, right? I definitely perform at least log delta hops, right? Well, up to a certain constant factor here. And therefore, I will definitely be able to guarantee a returnable answer. All right, so that's how things are going to work. Okay, cool. All right, so that's our goal. And the rest of today's talk is to prove this. Okay, the rest of today's talk is to, prove this formula. Okay. All right, now we will need a technical lemma together. Okay, so here, so let's say lemma 1. So this is a technical lemma. So we will prove the following. This, for any I, okay, at least 0. Okay, we definitely have. Okay, I forgot something. I have to define something first before this lemma. Okay. All right, so I will introduce some notations. Let's say P0. Now pay attention to the subscript here. Okay, P0. So P0 is the start point, the starting point that you give me, okay? And then the algorithm, greedy, accesses P1, P2, all the way to, I don't know, some PI. I can be as large as possible, right? So in other words, the first point access is P0, and then the second point access is P1. The third point access is P2, and so on and so forth. Okay. All right, now I can introduce this technical lemma that I need. So for for any I basically, this is going to be true. Okay, Pi Q, okay, is less than or equal to D P0 Q over alpha to the power of I, and then plus, alpha plus 1 over alpha minus 1. Okay. And here we have P star Q. Now, what is this star? I mean, every time you see this star appearing, this means optimality. Okay, so this is the exact nearest neighbor of Q. Okay. So before I prove this lemma, let's understand it better. Okay. So as you can see, we've got two terms here. Okay, we've got two terms. Now, with our choice of alpha, as you can see, our choice is here, right? So alpha is 1 plus 4 over epsilon. With our choice here, you can do the math and you can convince yourself that this is equivalent to 1 plus epsilon over 2. Okay, 1 plus over 2. So if you look at the whole term, this is not something that you can improve on by continuing greedy. You see what I'm saying? Because by continuing greedy, you can increase this I only, and therefore the denominator of the first term gets smaller and smaller. Okay. On the other hand, as you can see, if you increase the value of I, and then the first term is going to get smaller and smaller, right? So as you will see later on, after we have managed to establish this lemma, our eventual goal is to set this term here, roughly to epsilon over 2, roughly epsilon over 2 times D, P star Q. As you can see here, I purpose on purpose, right? I have this epsilon over 2 here, and our allowed distance is 1 plus epsilon times D, okay, P star Q, right? So here I have a leeway here, a slack. So I'll be able to utilize this slack. And I indeed, I will utilize it in this way. Okay, so I will choose this I to be large enough so that the first term is, basically bounded, okay, bounded by epsilon over 2 times the exact nearest distance. Okay, so that I can guarantee that the current PI is a returnable answer. So this is what's going to happen. All right, so let's prove the lemma. So this is going to be quite technical. So I'm going to walk you through the details slowly. Well, first of all, let's look at the base case. By the way, I will prove the lemma by induction. Okay, so if I is 0, and then as you can see, the left-hand side is just P0 Q, right? But on the right-hand side, the first term here, as you can see, the first term here, right? So this is, the denominator alpha to the power of 0, so that's just 1. And therefore, the left-hand side is already appearing here, all right? So it's easy to verify that this is true, okay? Now, let's look at the induction case, okay? So assuming that, let's say, assuming correctness for K, I, B, and K. All right. So now we'll prove correctness for I, B, and K plus 1. All right. So that's what we're gonna do. Good. All right. So PI is our previous hop, and sorry, PK was our previous hub, and the next hub is pk plus 1. So let's consider two possibilities, right? So the first possibility says that this pk plus 1 happens to be p star directly. Okay. So if this is the case, now let's look at the inequality, right? So in that case, this term on the left-hand side is going to be exactly, p star q, right? And this p star q appears here. And as you can see, the coefficient in front of it is greater than 1, right? Because epsilon is strictly larger than 0. And therefore, in this case, checked, right? So this cool. So it remains to discuss, the other case where this pk plus 1 is not p star. All right, so let's see what happens here. Okay. Now it's time to apply the shortcut property. Now, once again, let's bring out, the familiar figure, right? So let's say this is pk, right? So p star is here, and we know p star is not an out neighbor of pk, right? Why? Because otherwise, the greedy algorithm would definitely pick p star, but it does not. Okay, so p star cannot be, an out neighbor of pk. All right, and in that case, the shortcut property promises an out neighbor of pk. Okay, it promises us an out neighbor of pk with the requirement that the distance from u to p star is at most 1 over alpha. Okay, 1 over alpha, the distance of pk to p star. Okay, so this is what's happening. Now let's start a string of derivation. So here we've got pk plus 1 q. Now this is something we need to place an upper bound event on eventually. Okay, place an upper bound on eventually. All right. So what we can do is first we can observe that this is less than or equal to duq, right? Why? Because look, the greedy algorithm will pick the best out neighbor with respect to q. You see what I'm saying? However, the algorithm could pick u, but now it picks pk plus 1. So this means that the distance from pk plus 1 to q cannot be worse than the distance from u to q, right? So that's why this inequality holds. So next we will apply triangle inequality by using p star as the bridge. So now we've got this p star here, okay, p star q, right? So now p star q starts to come into the picture, all right? And now we can apply, this triangle. No, sorry, we can apply this shortcut property here. All right, so we know that this is strictly less. Okay, strictly less than 1 over alpha times d, and then p k p star. Okay, so this is one more step. All right. Now, so I would use, eventually I would like to use induction, right? Our inductive assumption to deal with pk. But the thing is, if you look at our target inequality, it's always, a distance with respect to q, right? But this is p star here, so we are not ready to use our inductive assumption yet. Which is why we have to proceed, with another triangle inequality, application of triangle inequality. So I'm going to use, this time I'm going to use q as the bridge. All right, so now this is over alpha, and then plus d p star q, right? Okay, cool. Now let's rearrange the terms a little bit. So this is d p k q over alpha, and then plus, this p star thing, and then times 1 plus 1 over alpha. Okay, good. Very nice. Now we can happily apply our inductive assumption. So we know that this is 1 over alpha, and then inside this term, this is at most d pkq, and then over alpha to the power of k, right? And then, don't forget we have this alpha plus 1 over alpha minus 1 here, and then this is dp star q. All right, so we have dp star q 1 plus 1 over alpha from above. Okay, good. Now let's massage the expression a little bit. Okay, so here we have what we want. This is alpha k plus 1. Sorry for the ugly alpha. Okay, k plus 1 now. And then we have something extremely long for this p star q. Okay, so let's be patient. Let's write them out correctly. So this is alpha times alpha minus 1, and then what? And then plus 1, and then 1 over alpha. Okay, all right. Okay, pretty long, right? Well, guess what? We're in luck. So this term here, okay, so if you simplify it, okay, this term here, it turns out to be, something we like to see. Okay, so this is precisely alpha plus 1 over alpha minus 1. Okay, so this is exactly what we try to prove inductively. Okay, and therefore this completes the proof of technical lemma. Okay, all right. Sounds reasonable, right? So sounds correct, right? Okay. Very nice. Okay, so now let's continue based on this lemma. Okay, so I told you before, you don't really have to remember this alpha plus 1 over alpha minus 1. Okay, so with our choice of alpha, you can rewrite this inequality into some slightly more friendly form. Okay, so this is the form we're talking about. Okay, p0q over alpha to the power of I, and then plus 1 over 1 plus epsilon over 2, and then this d p star q. Okay, so this is what we have currently. Now remember, as long as you get to pi, and then this pi definitely satisfies this inequality. Okay, cool. All right, so I'm going to prove the most important lemma. So so the lemma says log delta steps suffice. Okay, but before I continue, I would like you to understand the intuition. Okay, as you will see, there are 3 cases. We will see 3 cases there. Okay, however, if you just look at the proof directly, you might be wondering, how people thought about, creating those cases. All right. So here it's very important to grasp the intuition, and then once you have grasped the intuition, you would be able to derive the details by yourself as well. Okay, and probably you would do something different in the same direction. Okay. So look. Let me first tell you, I have already explained to you before that, we would like this term to be bounded by epsilon over 2, and then, d p star q, right? Okay, so I cut myself a slack here, as you can see, epsilon over 2, right? So this is something I explained before. So the good news is that this is definitely doable because, all you have to do is to increase the value of I, right? So this is going to go smaller and smaller for the first term. But the question is, if you move this thing around, this alpha to the power of I, is going to appear on the right-hand side, and this d p star q is going to be on the left-hand side, right? So you want to be able to bound the value of I. However, you will not be able to bound the value of I into bad cases, all right, troublemaker cases. The first case is, what if this initial distance is very large. You know, in the extreme, this can go to infinity. You see what I mean? All right. So if this is infinity, and then even if you take the log of infinity, the value of I can still be very, very large, right? And you won't be able to prove something like log delta, right? So this is one bad situation for us. Now, there is another bad situation. I mean, even if this is not very large, the initial distance, right? But what if this thing, you know, this P star, the distance from Q to P star, what if this term is very, very small? I mean, in the worst case, it can be zero, right? Q can coincide with P star, right? So the distance will be zero in that case. If that is the case, and then, you know, after taking the ratio, right, moving this d P star Q to the left-hand side, after taking the ratio, it's going to be an infinite value again, right? And, you know, again, you won't be able to prove this delta value. Which is why the proof will deal with three separate cases. All right, so basically three cases, right? The first case, what if the initial value is very large? And then another case, okay, the initial value is not very large, but what if, you know, the P star Q distance is very small? All right, and the remaining case, which is, you know, the most typical case, the initial distance is not very large, and also this P star Q is not very small. All right. So this is what we are going to do. Okay, this is what we're going to do next. Okay. All right, so let's start the proof. Okay, so let's look at case one. Case one deals with a bad situation. So this bad situation, you know, formula is this. All right, so if the initial distance says this is greater than 2 times d max. Okay, so let me explain to you intuitively what's happening here. You see, imagine that, you know, hole P is within this ball, right? So this ball has radius d max, right? So this is the largest interpoint distance, right? So basically, this is saying, you know, this Q is quite far away from this ball. Okay, so if that is the case, it could be that, you know, a lot of points inside this ball would be a returnable answer for Q. Okay, so indeed, as you will see, I can prove to you, as we will prove together later, that disk ANN, I mean this greedy algorithm, will find a returnable answer with just one hop. Okay, at most one hop. All right, so if the first guy is no good, and then the second guy will have to be good. All right. All right, now let's see it. Okay, so so we assume that P0 is no good. Okay, if P0 is already good, and then, you know, P1 will have to be good, right? Because the distance is strictly improved as you perform one hop, right? So we have already learned that. Okay. Now let's first look at the fact. Okay, so here I apply triangle inequality. So this P star Q. All right, so I can say this is greater than or equal to, you know, 0 Q and D P0 P star, right? So this is by triangle inequality. Okay. So we know that this you know, this term here, right? So this term is bounded. Okay, you know what? I'll write it like this. This term is bounded by D max. All right, so this term is bounded by D max, and therefore we know that this is larger than or equal to, you know, this value here, and then I subtract something large, right? So the direction holds, right? Larger than or equal to. Okay, good. And now I can utilize, you know, this inequality here. All right, so this inequality, now I can, you know, this is strictly larger than what? This is strictly larger than P0Q or 2, right? So I once again I subtract something large. Okay, so all right. So as you can see, this P0Q, as I told you, right? So this is at least 2 times D max, right? So if you look at D max, right? Okay, so this is really, really huge. Okay. All right, now look at this inequality. This is our valuable inequality, right? So let's apply valuable thing for I being 1. It's just one hop, and let's see what happens, right? So in this case, we've got this P1Q less than or equal to this D P0 Q. All right. So this D P0Q, we already know this. We can actually replace this D0. We can actually replace this part by. We can replace this part. Let me see. We can replace this part by 2 times. This 2 times P star Q, right? Because we have just proved, this thing is strictly less than this thing, right? Okay, so this is something we will do later. Okay. Anyway, so let me write down the inequality first. This is divided by alpha, and then 1 plus 1 plus epsilon over 2. Okay, and then this D P star Q. So this is what we have. Okay, so if we apply this thing, and then we have this is less than or equal to D P star Q, and then inside we have 2 over alpha, and then plus 1 plus epsilon over 2. Okay. So I'm not going to do the math for you, but you can convince yourself that with our choice of alpha, this is bounded by 1 plus epsilon. Okay, so you can do this by yourself. All right. So what this is telling us is that P1 is good enough. All right, so P1 is definitely a 1 plus epsilon ANN. Okay. All right, so this is the first case, right? Now, next, let's look at the second case. Now, the second case, basically, looks at a scenario where case 1 does not apply, right? So immediately we have this dP0Q. This is bounded by 2 times D max, okay? And also, I do not want this P star Q to be too small. So this is the typical case. All right, we started with an atypical case, and then the second case is the most common and typical case. And then later on, case 3 is going to be another atypical case. Okay. So here, what we will have is we require this P star Q to be at least D min over 2 epsilon plus 4. Okay, 2 epsilon plus 4. Okay, so this is not very, very small. Okay. All right, so now let's see what happens. Okay, so again, I argue that this I does not have to be very large. Okay, so indeed, let's say we will apply this valuable inequality there. So now we know this PIQ is less than or equal to, let's just copy that, P0Q over alpha to the power of I, and then plus 1 plus epsilon over 2, and then D P star QQ. All right, that's cool, right? So what we want, we'll do, okay, so we want to make sure that, this term, this term here, okay? So we want to make sure that this term, let's make it down here. You know what? Let's do one more step first. Okay, let's do one more step. So I'll replace this dP0Q with, this inequality here, so that I can have D max in the picture, right? Before I did not have D max in the picture yet. Okay, so I will copy this part from above. Okay, good. Now, so what we're going to do is we will make sure that this term, okay, this term, we want that to at most this thing, just epsilon over 2, and then 2 epsilon plus 4 in the denominator, and then d min. Okay, so this is something we want. Okay, so we will solve I from this inequality here. Okay, so let's say if so, all right, if we manage to do so, and then what can we obtain from here, right? So if so, all right, so let's say we indeed manage to achieve this with some I, right? And then this is going to be less than or equal to, epsilon over 2, and then 2 epsilon plus 4. How do we deal with d min? As you can see, this d min is less than or equal to, d p star q, right? And multiplied by this 2 epsilon plus 4, which now appears in the numerator, which is great because that will cancel out the 2 epsilon plus 4 in the denominator, right? So this is 1, so 2, and then p star q, right? So now you can see this is essentially what we want to have, right? So we have this epsilon over 2 there, and we have another epsilon over 2 here. So eventually we get 1 plus epsilon, right? Okay, cool. Okay, so if this is the case, then all good, right? So now it suffices to look at this inequality, right? So this inequality basically says, this alpha I. Okay, you know what? Let me copy this over. So this d max over alpha to the power of I less than or equal to epsilon over 2, and then 2 epsilon plus 4, and then d min, right? So now this is telling us, alpha to the power of I will have to be larger than or equal to, let me see, this is, let me see, 4, actually 8, epsilon plus 2. Okay. And I've got this epsilon here, and also I have d max over d min, right? So that's just delta. Okay. So this is what I have. Okay. So that tells us that, I will have to be at least this much, right? So log, so I will write it like this to be useful later, as you will see. Okay, so this is plus log delta. And then here I will write log alpha. Okay, alpha is just 1 plus 4 over epsilon, right? So this is what we have here. Okay. So in order to analyze this thing, I'm going to make an assumption. So I'm going to make an assumption that epsilon is no more than 4. Okay, so if this is the case, then 1 plus 4 over epsilon is at least 2, right? So this is alpha. So usually when we make an assumption, it's bad news, okay? Because when we do theoretical analysis, we don't want to make assumptions, right? However, is this really an assumption? Or this is something, non-harmful? Are we losing any generality? So basically with epsilon at most 4, we're telling people, you can only do 5 approximate nearest neighbor. So if you want to do 6, what do we do? What do we do? Well, we say, you know what? You want to do 6 approximate, right? And I give you, I provide better service for free, okay? Because now all I want to prove is that I will be able to finish in log delta steps, as you can see, right? So I'll prove to you, you perform log delta steps, and I give you something better than what you hope for, right? So if epsilon was 5, and then I just manually decrease it to 4, and then apply the analysis. Okay. All right, so if that is the case, and then we know that there are 2 terms here, right? So the first term, this is so let's work on this fraction here, right? So this is essentially just 8 plus 2 over epsilon, and then we have this log 1 plus 4 over epsilon here, and then we have log delta, and then this log 1 plus 4 over epsilon, right? So we know this term right? If the, well, if 1 plus 4 over epsilon is so we know that this is at least this is big O of log delta over log 2, right? So this is just log delta, right? Okay, now how about the first term, right? We still have to worry about the first term, okay? So I will leave it as an exercise for you to, oh, by the way, here, this is 16, right? So this is 16 here. Let's correct it. This is not 2. This is 16, right? 2 times 8, right? Okay, so I'll leave it as an exercise for you to figure out, to prove yourself that this is bounded by the constant, okay? So here is a sketch of the proof. You want to consider 2 possibilities, right? So think about this 1 over epsilon. Let's say you want to distinguish 2 cases. Is this larger than or equal to 1, right? And another case is, let's say, less than or equal to 1, right? So you want to analyze these 2 cases separately, okay? All right. So basically in the first, and then you will only have 1 over epsilon. So that will be the dominating term. But then for the second case, you will not have 1 over epsilon, right? So that's the idea, okay? But I will not go into the details of this, all right? Okay, so what have I shown? As you can see, as long as I is, at least this number, right? It doesn't have to be greater than this number. So this number is simply, the whole thing is constant plus log delta, right? So that essentially tells you, after log delta steps, you are good. You are good in the sense that, you have found a returnable answer. All right, so that case 2. Okay, good. Now, finally, let's look at the remaining case, right? So case 3. So this case 3, basically picks up where we left off in case 2, right? So, we still have this condition, all right? All right, so we still have this condition, but then the remaining piece of the logic we have not really accounted for is this, right? So this P star Q is something quite small, right? So this is less than 2 epsilon, sorry, d min over 2 epsilon plus 4. Okay, by the way, this is as a corollary, right? So this means less than d min over 4. Okay. All right, so we will prove in this case, this KNN still works. So let me show you what's going on here. You see, this time we want to zoom into the data set. Basically, d min says the interpoint distance is at least d min, right? Now, since this P star Q is so close to Q, and then essentially the situation we're looking at is something like this. The current point is in here. You see what I'm saying? So current point is very close to its nearest neighbor compared to all other points. Okay. So in this case, I will prove to you that not only this ANN will be able to find you a returnable answer, but even better, it's able to find you the exact nearest neighbor. Okay. And let's see why this is the case. I'm going to prove this to you. Well, I would need a fact. All right, I would need a fact. Okay, so I will show you, right? So if you have considered any point, pi. Okay, so pi is a point that is accessed by the greedy algorithm, right? So if this pi is not p star, okay, if this pi is not p star, then you definitely have the following. Okay, so let's apply triangle inequality. Okay, so this PIQ is, sorry, this PIQ is, at least this PI, P star, and then minus, P star Q. Okay, and we know the first term, this is at least d min, right? Because this is interpoint distance. But on the other hand, we know that the second term is bounded by d min over 4, right? So now we know that this is at least, d min 3 over 4. Okay, in other words, basically you can imagine that, we can divide the data set into two parts, only P star in the first part and then everybody else in the second part. Okay, and P star, of course, the distance is something very small, less than d mean over 4, but all the other points, their distances to Q are at least 3 over 4 times d mean. Okay, cool. Now, once again, we want to apply our valuable inequality. Okay, now on the other hand, right? So on the other hand, right? So we want to apply our valuable inequality. Okay, so let me copy it here. So PIQ less than or equal to, this is P0Q, and then over alpha to the power of I, and then plus 1 plus epsilon over 2, and then d P star Q, right? Okay, so now I can zoom into here. All right, so don't forget for this P0Q, we have something nice, right? So you can see we are working under that condition, all right? So I'm going to apply that later, right? But just so you know, for this P star Q, right? So for P star Q, we also have something nice, right? So this is also bounded now. So applying those two things, now we have, applying those two things, now we have, from the above inequality, we have a new inequality. Okay, and this is 1 plus epsilon 2, and then d min over 2 epsilon plus 4. Okay. Hey, what is this term, right? So you can see this, obviously this can be simplified, right? So this is simply d min over 4. Okay, d min over 4. All right, now what we want is to, so we want this term, the first term. We want to choose a value I that is large enough so that this becomes, bounded by d min over 2. Okay, so let's say we have already chosen this value of I so that this thing happens. Okay, and then we'll come back to analyze how large this value of I really needs to be. Okay, so if this is true, right? If so, let's say, right? And then we can continue from above by saying, this is d min over 2 and then plus d min over 4, right? So this will give us 3 over 4 times d min. Okay. All right. So now this says something interesting. Look, here I have got something, like at least 3 over 4 times d min, right? So here, let me see. Actually, here, I'm sorry. So this inequality here, so let me undo it. Look, this inequality here is actually, strictly speaking, is actually a mistake, right? Because here, as you can see, we have strictly less than, right? So I should have put, actually, this is important, right? So this is strictly larger, okay? Strictly larger than 3 over 4. Okay, all right, so I just corrected myself. Now here is something interesting, right? So you see here I said if Pi is not P star, and then it will have to be strictly larger than 3 over 4 times d min. But then I say, okay, after this I becomes sufficiently large, the distance will be at most 3 over 4 times d min. So as I told you, right? So you can imagine as if the data set was divided into two parts, right? So the first part contains only P star, and the second part contains everything else. And in the second part, all the points satisfy this inequality. So therefore, when this inequality has to hold, and then there's only one possibility. So this point must be P star. Okay, must be P star. All right, good. So now we are close to success, right? So all that remains to do is to find a value of I to make sure that this thing holds. Okay, but this is pretty easy. Now let's see what this inequality tells us. So this is essentially saying alpha I would have to be, at least 4 times d max over d min, so that's just 4 delta, right? So I can be log alpha at 4 delta, right? But I told you, alpha is at least 2, right? So all you have to do, suffices, right? So I can be set to, let's say, ceiling of this guy, and this guy is just, log delta, right? Good. All right, so it's a long proof, and I hope you have enjoyed it. Okay, but as you can see, the whole proof tells us that, after log delta steps, no matter what, right? No matter if you, whatever you do, whatever starting point you choose, right? You always find a returnable solution. All right. So this proves that the whole algorithm. Actually, I should have said this proximity graph created by DiskKNN is able to guarantee a query time of this. Okay, according to our definition Q. Okay. All right. So that's everything I have for today. Thank you for listening.